Good afternoon, everybody. I'm Eric Ostby, the new Chief Product Officer at Aliro. It is bright, as everyone said. Let me come on over here for you. Good, thank you. I joined Aliro this summer, previously with Rigetti. I have some Rigetti colleagues here, and Google Quantum, Google colleagues as well. So it's great to be here with a lot of friends and colleagues. So today, I'd like to talk with you about networking QPUs. I think everyone, it's been on people's minds, especially lately, and just share some thoughts about this and a little bit of call to action for us, and then a little bit about Aliro, Quantum, and what we do and how we can help too. But I'm not going to give you a big sales pitch. That's for my colleagues' jobs. So I'll talk through networking quantum computers and the two main types that I see: clusters, which is the more immediate need, and longer-term distributed quantum computing. Give a call to action, highlight some of the recent developments in the space. Cover briefly just Aliro Quantum. We're a software networking company, so we make software and services to help people design, build, operate, and optimize their quantum networks. And at the end, hopefully have a time for some questions. It's always really rich. So I was a late addition to this schedule. I'm pleased to be here, but this is a dialogue. So welcome your feedback or suggestions. I really want to stimulate not just, it's not about my presentations, it's about your thoughts, your ideas, the conversations that we have, that you have with each other afterwards, and what comes next. So just briefly, Aliro, we focus on entanglement-based quantum networking. There's different types. There's prepare and measure, QKD. We've had some good presentations today already. Noel had a great presentation about the excellent hardware products that are offered by Connect. We do work with Connect and appreciate the call out there on your slide. And so for us, we focus not on distributing keys that are generated through a quantum mechanical process, but actually entanglement between nodes and setting that across multiple nodes and using that to share keys or transmit data. The data rates are low today. The figures from Noel were excellent, but this is the photon generation transmission actually running a protocol. A QKD protocol has overhead, and it does drive those data rates down, and it's a stochastic process to generate these photon pairs, not deterministic, and so it does impact those data rates. But we talk about the value of quantum networking based on entanglement being that eavesdropping protection, that you detect if that entanglement is broken and someone has been eavesdropping. Some of the applications on the bottom, sharing secrets, transmission that doesn't need to go through a public network. In the middle, we'll talk more about today the entangling qubits on different QPU chips or at a distance between different quantum computers, and then transmitting those qubits through teleportation down the line. So on the left here to start, I think we have an urgent need together. We've had really good announcements. Exciting yesterday, IBM announced the System 2, which is actually 3 cryostats, 133 qubits each, so close to 400, 399 total. My understanding is that these are directly connected through superconducting wires, cables, coax cables through a vacuum tube, which makes sense, and I think it's a great achievement to show that. That is, I would argue, not the scalable solution long term, and so I come from a photonics background, and I think the photonics will have to be a part of the solution at some point. We'll see how far we can push it, but the first need is really to network together the QPUs. So at Rigetti, at IBM, at IonQ, we call these quantum computers, but you could also see them as a QPU, kind of like a GPU. You're going to need many of them, likely, to have a very powerful quantum computer and realize the promises that we all share. And I show some examples here from different companies of their vision of a quantum computer cluster. The reality is I think we do need a photonic solution as we scale these, and I'll show some numbers later about how many we may need. On the right side, distributed quantum computing is when you actually have likely an error-corrected quantum computer in one location. Let's say it's in New York at Gotham Q, and you want to connect that to another quantum computer that's error-corrected at Caltech, where I went to school, for example. That is distributed quantum computing. There's different use cases there. That's a bit further in the future, so I'm not going to focus too much today on that. And the map just shows some of the quantum networks, and Gotham Q is on there as well. So there's going to be an evolution, naturally, of quantum networking. We're starting initially with point-to-point, these endpoints to endpoints. We'll start to cluster those, and you're starting to see these at like the EPB network in Chattanooga, Tennessee, where Aliro has deployed its software solution. We're all waiting for that repeater. So Connect is working on it. Other companies, I'll have a slide on a few of those to allow us to actually based on a quantum memory, extend the transmit distance beyond, as we saw, 20 to 50 kilometers, maybe closer to 100 if you're lucky. And then a chain of repeaters naturally to go beyond kind of a metro area and on to having a network based on quantum routers at the bottom here. And then in the future, a quantum internet, which is a big dream for all of us. I'd like to just point out that quantum internet is not going to replace the internet we have today. It's going to be by the side. It's going to be specialized, just like quantum computing. It's going to be targeted at specific tasks. It's going to be lower volume because it needs to be. It's certainly not, the vision is not to transmit all of our data over the quantum internet, but we see it as a very powerful, likely necessary network to push forward computing and hopefully human consciousness as well. So when you talk about, and looks like the PDF converted the slide. This is supposed to be a 2x2 matrix. I did work at the Boston Consulting Group. So draw that line, flip one of them by 90 degrees, plotting horizontally from left low to right high scalable qubit maturity. It's my own metric, but it's a sense of how mature are the qubits, how scalable are they. On the vertical axis, low to high is networking difficulty. So just a quick view of my view of how challenging it is to have likely a photonic integration for a network. On the top right, superconducting, we have a lot of great developments and companies here working on superconducting qubits. They are a very scalable, arguably very scalable technology that's been shown. I'm sure the photonics group will disagree, but there's a maturity level there, right, in the qubits and in their scalability that's been shown, like with the example by IBM yesterday. Lower on qubit maturity, I would argue, is photonics. So PsiQuantum does excellent work, strong team, and I think they have a good architecture. They need a special beam splitter they're working on, which is really important, but they also were waiting to see the qubits and see that computation, which I'm sure will come, and they'll probably zoom to the right, which is what I hope will happen, and we'll have a good, healthy competition of different architectures. Neutral atoms, trapped ions, they have a photonic integration with the way that they're set up and controlled with optical tweezers and readout, but the state is still in the electronic structure of that atom or that ion, so it's partially addressable. There's still some transduction that's needed. Quantum dots and spin qubits are kind of in the middle. I didn't have a strong reason to put them any one direction there, but I wanted to call out that they're likely harder to have transduction and optical interconnect, and they're not quite as mature on the qubit scalability standpoint. But it's important to think about these things as we look, and now I'm a little bit free being at Aliro to work with everyone, really, and let's find a way to start networking these QPUs together. So the call to action really is that today, I give an example of superconducting qubits because it's one that I know particularly well. We have a rough kind of industry best in terms of the physical qubits and logical error rates, the error rates, the gate speeds, etc. That's where we are today. You know, squint at it, it's roughly right. On the right side is where, again, this is my view, and it's certainly wrong. There's different opinions, but order of magnitude, useful quantum computing, where is that going to be? You're going to need an immense scaling, right, in terms of number of qubits. You're going to likely need error correction to realize many applications. I hope there's applications in the NISQ era in the production, and I'm cheering for that. Error rates will need to be a lot lower as well. So how do you get from today to tomorrow? IBM's taking steps in that direction, and I&Q has talked about their work and necessary to have networking, but we need to cross that chasm, right? And we need to do it. We need to start today, I would argue, because it'll give us information about the system requirements that we need. So to give some examples of the developments, I was at Photonics West, and Peter Chapman talked about photonically interconnecting their quantum systems, and I'm sure they're working on this, and I know they are because they had a good acquisition of a Canadian company to help them with this. But again, it's a slide today, and that needs to become a reality, right? That you can integrate and network multiple QPUs together. On the bottom right, IBM gave a roadmap. I had to submit my slides last week, so this is old. They have a new, very dense roadmap. But in it, they talk about connecting multiple chips, but they don't say anything about photonics. From reading their latest announcements yesterday, it doesn't sound like the photonics is in their current plan. They talk about the high density interconnect. It seems to be microwave based. So I'm excited to see how far they can push that. My hypothesis is that they'll need to go to a photonic solution at some point. Wanted to switch from kind of the commercial era to then the call to action from the government too. Last year, I'm not sure if David Rivas is in the crowd, but at Rigetti, we had a chance to respond to a request for information from DOE about how would you integrate a QPU into a supercompute facility like Ornell Summit or Frontier. And I got to work on that. I spent a good week and probably close to 100 hours on that proposal, but it got me further down the road to think about how would you actually do that. There's a lot of concerns of, how would you do the networking, of course? How would you have the physical location? How would you upgrade and maintain? And that's coming because the DOE said their time frame for considering accelerators like QPU was 2026 to 2030, and that's just around the corner. And Department of Energy has been also doing investment in different programs into quantum networks. Many of you probably are working on these programs. They're excellent, but it's clear to me that we need to provide and make steps towards a solution to actually integrate QPUs into a data center, a classical data center, eventually a facility as well. So I think we need to get working. My pitch today to everyone is that let's get started on this as soon as we can. Aliro is here to help. It's going to require many hands and many technologies to realize this. Number one, QPUs are stable enough to start to cluster, right? You look at the uptime statistics that were shared, the IBM has shared and IonQ has shared. I know the ones from Rigetti and Google as well, and they are now stable enough that we can actually start to cluster these and set up networking. We don't require repeaters to do this. It's all in the same building, and so that's very feasible, although the repeaters will extend those distances to make things easier. There's varying levels of optical transduction. So you saw that 2x2 chart I shared. Some are easier, some are really hard, and I think we need to tackle all of these. I just talked to a gentleman today from Switzerland who's working on a transducer based on lithium niobate crystals to do the optical to mechanical, optical to electrical transduction. So a lot of exciting investments. Some are easier, some are harder. The harder ones we definitely need to get working today. Some of the QPU architectures are already photonically integrated. So PsiQuantum, Xanadu, IonQ, Quantinium, for example, there's already the photonic component. Now, some are going to be more difficult versus a little bit easier, but I think we can get started today. And I'm sure that a number of them are working on that, which is great. And we have some conversations with them. Finally, I think it's really critical that we start today because we'll get data to understand the limits, right? Of, okay, if we actually set up a network with 4 QPUs in a data center, here is the conversion efficiency, here is the fidelity, here are the loss rates. It's going to give us data on like, well, actually, how many qubits should you put on a chip, right? Okay, we have confidence we can do a cluster of 4 QPUs, but we really can't do 8. That tells you how many you have to get onto one of your chips. So I think we need to start this soon so we can understand those requirements to build a system at scale. Repeaters, we watched this very closely at Aliro. There was some talk from Noel about this as different systems. I won't go through them all. Solid state versus atomic. Most of them have a cryo component that does introduce some challenges, but many quantum solutions have a cryo component. And of course, the optical systems too that I think are very exciting. So what you'll need to make a repeater will need a quantum memory of certain specifications. So it's really almost a holy grail device that we're all cheering for, and there's development going on. So there's a number of companies, I'm sure I've left off some new ones here, that are working on quantum memory, so we should all cheer for them and fund them and support them, and Aliro keeps in touch with these companies too to watch the latest and greatest. So a little bit about Aliro at the end, saved at the end, not to bore you too much, but I joined Aliro really to work on another piece of the puzzle, right? To build useful quantum technologies in addition to sensing. So the networking component is critical. In some ways, networking is more mature in some areas than computing, and so it has some advantages. Aliro was founded 4 years ago, spun out of Harvard by Preena Rang, who's currently now at UCLA, which is not too far from where I live. The mission is really to enable multi-purpose entanglement-based quantum networks and their solutions. Our business model is software and services. We're not a hardware company, although we got a request last week to build a Linux and FPA solution to serve as a controller for a quantum network because no one has one. So stay tuned. Our focus is on software. We prefer to partner with people to build the hardware, but again, startups have to be agile. We have supporting from US VCs. We just raised our Series A, which included Cisco and Accenture. We're great partners. We have weekly calls with them and building kind of a go-to-market together and helping educate each other on those possibilities. I think, I don't know if Corey's in the crowd, but we have deployed in partnership with Qubitekk to EPB our orchestrator software solution to help define and manage and operate the quantum network. And EPB has the first user configurable commercial quantum network in the US. And you should go see it. It's in Chattanooga, Tennessee. A little bit about our funding, a couple words of support from some of the key leaders at Cisco and Accenture. They're good partners. Our current offering, I joined 4 months ago, and so I think there'll be some natural evolution. We have a strong series of products. Of course, as a startup, you always have to decide where do you prioritize, where do you focus. We offer a simulator. We'll have more announcements coming soon. We already are in a trusted tester phase where we have it's a physical, down to the physical optical level simulator of a quantum network. It's a discrete time-based event simulator. It has on its back end Circ as well as other backends. And we're using it with customers today to provide blueprints for quantum networks. So you're designing a network. What are the trade-offs? What should your node design be? How many nodes should you use? What hardware should you test? And it has the capability to put in both you have ideal devices, and we also have the ability to put in a custom noise model for a specific real device. So it's quite powerful. It's quite technical. It's at the advanced level. We offer a simulator as a service that we have a number of customers interested in and that we're selling today. That's the simulator. Orchestrator deployed at EPB. It allows you to define, configure, manage your quantum network. It's not feature complete, but it has the core components, and we're continuing to build on it in collaboration with EPB and Qubitekk. And Aliros is not released yet, but it is our software layer that is more tuned to both the application layer, so running protocols, error correction, network management services, as well as being able to go down, if needed, to the device level and have code that could be on the device if our partners would like that or benefit from that. We are hardware agnostic, but we have hardware partners. We're not sole focus on any one of them. We want our customers to have the best hardware solutions. And we offer a number of services around network design, testing verification, protocol development, et cetera. We have a strong team of network experts, both classical and quantum. Okay, close to the end here. The use cases we target, so I've talked to a number of you today, and this came up. We're getting a lot of interest right now on secure communications. So we heard great talks about QKD. We focus on entanglement-based secure comms, including direct secure comms. Quantum computing is close to my heart, and it is definitely, I would say, an intermediate use case that's very important. That's why I'm talking about it today. Distributed quantum sensing is something I haven't personally delved too deeply into yet, but it's on my roadmap, and there's a lot of interest to see what we can do with networking clocks together, for examples, and sensors, other types of sensors. And then, of course, building towards long-term the quantum internet once we get the repeater and we can start to put together these networks and operate them. Just a graphical view of our product. I talked about the simulator, the orchestrator, our controller. So the orchestrator and controller have APIs that are used, and then we have Aliros, which is a flexible lower-level code that's used both for applications but also device integration. Excited, we announced a couple months ago with Qubitekk deployed with EPB. You should go visit. It's really a special place, not only for the quantum network, but just the innovation that's happening at EPB. So definitely, I haven't been there yet. It's on my schedule to go visit, but really proud of that partnership and how it's going. And that's it. So time for questions. Thank you very much for your attention.
Great. Thank you, Eric.
Yeah.
Any questions?
And corrections and disagreements. It's all welcome.
Hey, Eric, you had a slide that showed
you
had a slide that showed the kind of 2D-ish
I
plot.
knew I was going to get in trouble.
No question on that, because you kind of talked about the two different axes there. Question for you on Aliro Net and how you adjust your approach, or how difficult or easy it is depending on the different types of qubits.
Yeah, good question. Well, it's kind of fortunate as a software company. It's not as much our problem as long as those transducers exist and the memories exist as well. So I would say it's a great question. How do we adjust what we do? I think we want to be kind of the full life cycle. So we do actually keep in touch and work with the devices that are not yet production grade, like quantum memories and transducers, but also we work with Qubitex and Connects devices that are here today. So for us, the more immature a technology, we would like to get involved earlier, because we have a chance to work together and kind of influence, how is this device, programmed? What is the communication language that's used? Is it serial port? Is it USB? Is it Yang, et cetera? And so the earlier the better for us. And our vision actually is that and I hope to build this, we actually are a bit of a test bed, like Connect talked about their test bed for user applications, where it could be a test bed for devices to come and be tested in a quantum network to say, okay, swap this one in, this one out. Okay, update the software, what needs to change? So it's a great question. And I think for us, the earlier that we get involved, the better. When something is really kind of fit and finished and shipped, integrating that, we have to do some extra work. Our idea is to build libraries to actually make that ease of integration really strong. Personally, I think I'd love to work with the superconducting companies, and we have spoken with them. Likely the photonically integrated ones are going to be maybe a little easier in the beginning, given that they have an infrastructure in place. We're waiting for that transducer really for the superconducting. And actually, when I was at Google, I wrote a support letter for some research in that area. So thanks for the question.